Delaware Tech, Chemistry 100, Chemistry 110, Unit 5 continued, balancing chemical equations. Whenever we balance chemical equations, we want to make sure that the number of each atom on the left side of the equation equals the number of each atom on the right side of the chemical equations. And that involves determining what the ratio of each substance is within the chemical reaction so that all of the atoms are the same on the left and the right. So remember, atoms can't be destroyed, they can't be created during a chemical reaction. And because of that, a balance equation has to have the same number of atoms on the left as it does on the right. The balance equation represents a fixed ratio of reactants and products. We have no fractions. In other words, you can't say that a half of this molecule reacts with one of these to produce 3/4 of this. Everything has to be whole number ratios. For instance, I can have 2 of A reacting with 3 of B to produce 1C and 4D. That's a perfectly fine set of ratios. They're all whole numbers, and it's the lowest ratio of those. I can't simplify it anymore. So there are certain things you can never do when you're balancing equations. One of them is to never put a coefficient, this is telling you how many of the molecule, in the middle of the formula. In other words, it's okay to say 2 sodium chlorides are reacting or 2 sodium chlorides are products, but you can't say sodium 2 chloride. In other words, you can't double or triple part of the molecule without doubling or tripling the whole formula. You can never change a subscript in the formula for the substance in order to balance the equation. For example, I can't change iron with 3 sulfates to iron with 4 sulfites. That would change the formula. You can't just change subscripts. You can change the coefficient, the number of the whole compound, but you cannot change the formula of the compound itself. The joke is, 2 men walk into a bar. The first orders some H2O. The second says, sounds good, I'll have some H2O too. The second man dies. So here's a reaction. Carbon plus oxygen gas, O2, produces carbon dioxide, CO2. And you'll notice the number of carbon atoms on the left is just 1. The number of carbon atoms on the right is also 1, so that's balanced. The number of oxygen atoms on the left are 2 oxygen atoms, and on the right, also 2 oxygen atoms. So this equation is already balanced, so you don't have to do anything. Now in this equation, we have carbon plus oxygen gas produces carbon monoxide. And if I had 1 carbon plus 1 O2, that doesn't balance to give you 1 CO. Whereas in the first equation, 1 carbon plus 1 O2 does give me 1 CO2. It's already balanced. So we have to balance the second equation. And shown on the right here is a picture diagram of the carbon and an O2 molecule to make a CO molecule, carbon monoxide. And you can see right away, I don't have enough oxygens on the right side to balance the left side. So how do we fix that? Well, we can't just add an extra oxygen or change the formula of CO to CO2. That doesn't go with the rules. Instead, we can say, all right, we're not producing 1 CO molecule, we're producing 2 CO molecules, and that fixes the oxygens. We have 2 oxygen atoms on the left and 2 on the right. Unfortunately, that now messes up our ratio, our balance of carbon atoms. We only have 1 on the left and 2 on the right. So how do we fix that? Where do we get that extra carbon from? Well, we just add another carbon, so our actual reaction would be 2 carbons plus 1 O2 give us 2 COs. And you'll notice that the left side of the reaction has 2 carbon atoms, the right side has 2 carbon atoms, the left side has 2 oxygen atoms, the right side has 2 oxygen atoms, and this would be considered a balanced equation. Now, drawing pictures like this is not the most practical way to solve these, so I've come up with a strategy for balancing equations. It's what I call the hard, easy, easy, hard method. And I'll go through it. So first you're going to write your skeleton equation. You have to know the correct formulas of each compound to do that, but you're going to write the skeleton equation. Something plus something gives you something plus something, whatever. Okay, and then you can check to see if it's already balanced by making a table. You make a table counting up all the atoms of each type on the left and all the atoms of each type on the right. And then you start balancing. And how do you do that? Well, I have this strategy here. First, you're going to look for elements that appear in only one formula on the left and only one formula on the right. So you're looking for something that's only in one substance on the left and one on the right. We'll call these the easy ones to balance. You will then pick the hardest of the easy ones to balance first, and I'll show you what I mean by that when we get to actual examples. Once you balance the hardest of the easy ones, balance the other easy ones. Once you're done with all the easy ones, you now balance the hard ones. What are hard ones? Hard ones are ones that appear in two reactants or two products or more. If they appear in more than one reactant or more than one product, in other words, they appear more than one formula on the left or on the right, those will make that will make those very difficult to balance without other information. So you always want to do those absolutely last. So in the end, you might end up with numbers that are not whole numbers on the left and right side, and you always have to have whole numbers. So the way to get around that is to double all your values or triple all your values, or whatever number will make all of them whole numbers, but you want the lowest ratio of whole numbers. For instance, if I had two reactants giving two products, well, I can simplify that to one reactant and one product. So here's the review. You're going to do the harder, easy ones first, the easier, easy ones second, and then the true hard ones last. And then when you're done, make your table again and check to make sure that every element in there, every atom is balanced, if there's the same number on the left as on the right. So let's look at some examples. Here we have a number of examples of unbalanced chemical reactions, and let's go through them. So the strategy here is to first look for the easy ones versus the hard ones. And if we look at this equation and we kind of give ourselves a little line that divides the left side from the right side here, a little squiggly line, we can see that hydrogen appears in only one compound on the left and only one on the right. In fact, there is only one compound on the right. And oxygen appears in only one compound on the left and only one compound on the right. So they're both in the category of easy ones to balance. The hydrogen and oxygen are both easy. Which one will you balance first? You always balance the harder of the easy ones. Well, if we look at hydrogen, there are two atoms here and two atoms here. Well, that's going to be easy. Whatever number of hydrogen gases we have has to be the same number of waters that we have, because the H2s are on both sides. So we need to have the same number. So we'll do that one second. But the oxygen, however, there are two O atoms here and only one O atom here. So we want to figure out the coefficient, this number here for the oxygen, relative to the water. This has two O's in it. This has one O in it. So that means for every one of these, I need two of these. So now we know the ratio of oxygen to water, oxygen gas to water, is 1 to 2. That's fixed. It might end up being 2 to 4 or 3 to 6, but the ratio is still 1 to 2. That ratio is fixed. And now we know something about the hydrogen now. We have 4 atoms of hydrogen at this point on the right, and therefore that is enough to have 2 H2s on the left. And that we can rewrite this and check. Let me change here, and we can show the answer. And now you check, and you make your little table, and you can make your table right underneath, right here, and we can count up. And I know this is going to be sloppy, but you have hydrogens and oxygens here, and you'll notice you have 4 hydrogens here, you have 4 hydrogens here. And you have, and I'm going to write right on top of the other answer, I apologize, you have 2 oxygen atoms here, and you have 2 oxygen atoms here. and therefore both oxygens, that's actually the oxygen, and that's the oxygen, and now both atoms are balanced. And typically you want to give yourself more space than I gave myself here to make your table and check to make sure everything's balanced. The next equation is CH4. You can call this carbon tetrahydride. It's more commonly known as methane. This is what's in natural gas, and it reacts with O2. So this is a combustion reaction. You're burning methane in the presence of oxygen, and you're going to produce carbon dioxide gas and water. And the water will be water vapor initially. Eventually it'll cool down and become water as a liquid, but we're not going to worry about that for now. Now, you'll notice if we look at the carbon, it appears one time on the left and one time on the right. So that's an easy one. The hydrogen appears one time on the left and one time on the right. That's an easy one. So hydrogen and oxygen are both easy. Now, look at hydrogen and carbon are both easy. Oxygen appears only one time on the left, let me underline that, but two times on the right. So oxygen is a hard one. We're going to leave that to dead last to finish. So we've got carbon and hydrogen to do first. The carbon, you'll notice there's only one atom carbon here and one atom carbon here, so that's going to be easy to balance. Whatever this number is will be the exact same number as this one here. Whereas the hydrogen, we have 4 hydrogen atoms here and 2 here, so the hydrogen is going to be a little harder to balance. So let's balance the hydrogens first. We're going to look at methane and we're going to look at water, and we have to determine each one. Well, if we start with 1 methane, we have 4 hydrogen atoms. That is enough to make 2 waters. We have enough hydrogens to make 2 waters. How do we know? Well, that's 4 atoms of hydrogen, and that's 4 atoms of hydrogen. So we've balanced the hydrogen. Now let's look at the carbon. That's the easier of the easier of the easy ones. We have 1 carbon here, and so we can only make 1 CO2. We only have enough carbons to make a single CO2 because that has 1 carbon in it. Now we have enough information about how many oxygens we need to make our 2 products. So I'm going to erase these things here, and you'll notice that among the CO2, if in fact we had 2 of these and 1 of these and 1 of these, that means we need 2 oxygen atoms to make the 1 CO2, but we also need 2 oxygen atoms to make the 2 waters. That's a total of 4 oxygen atoms that we need. So how many O2s will provide 4 oxygen atoms? Well, 2 O2s, because 2 times the 2, will give us 4 oxygen atoms. And now we can check to make sure that everything is balanced. We would make our little table. We have the left side and the right side. This is our reactant side. This is our product side. And we've got carbon, hydrogen, and oxygen. On the left side, we have 1 carbon. On the right side, we have 1 carbon. On the left side, we have 4 hydrogens. On the right side, we have 4 hydrogens. On the left side, we have 4 oxygens. And on the right side, we have 2 plus 2 oxygens. So everything is balanced. That means we know we did the right answer. The only thing left to check would be to check to make sure our ratio of 1, 2, 1, 2 is as low as we can go. Is there anything we can divide all those numbers by and still have whole numbers? Well, we can't. We can't divide it by 2 because each of the ones will become 1/2. So this is the simplest ratio, and this would be our answer. And I'll just show you right here. That is our answer. 1 methane plus 2 oxygen gas molecules gives 1 molecule of carbon dioxide and 2 molecules of water. And in fact, a better way to describe this would be 1 mole of methane reacts with 2 moles of O2 to make 1 mole of CO2 and 2 moles of water. So a mole is our way of counting the molecules. We're just counting a lot more now. So if we look at the third example, we've got silver nitrate plus copper makes copper 2 nitrate plus silver. And you notice we have several things to balance here. We have the silver, we have the copper, but you'll also notice the nitrate, which I'm going to put a parentheses around. There's only 1 nitrate over here, and there are 2 nitrates over here. And since nitrate is not changing its identity, it's not breaking apart into nitrogen and oxygen, we can just balance nitrate as together as one object, just like silver and copper here. So there's no point in breaking it apart. We're just going to balance three things. And you'll notice in this reaction, all three things appear only one time on the left and only one time on the right. Silver is only one on the left, one on the right. Copper only one on the left, one on the right. Nitrate appears in only one substance on the left and one substance on the right, though there are two nitrates in that substance, but we're only counting how many substances it appears in. That is what tells us if they're easy or hard. And all three are easy. They appear in one substance only on each side. Now, because the silver to silver ratio of atoms is 1 to 1, the copper to copper ratio of atoms is 1 to 1, they're already balanced. They're easy to balance. So the only thing left would be the nitrate. The nitrate would be the harder one to balance. So the question is, how many of this compound versus how many of that compound? And if we have two nitrates over here, that means if we had one of these molecules, we need two of these molecules. I use the term molecule, but I really mean formula unit in this case. So now we know the ratio of those two substances. That's set. They might end up being double that. It might be 4 to 2 or 6 to 3, but the ratio is still 2 to 1. Nothing will change that. Now we have information. The 1 copper tells us, oh, I need 1 copper. And the 2 silver tells us that I need 2 silver products. And now I know that the final ratio is 2 silver nitrates plus 1 copper will give 1 copper 2 nitrate and 2 silvers. And I'll erase all these messy notes and show the answer here. And 2, 1, 1, 2, that's as simple a number ratio as I can get. I can't divide that by anything to make it simpler. Magnesium plus nitrogen gas makes magnesium nitride. And that's the formula for magnesium nitride. You would get it from using the crisscross simplify method, which we did in the last unit. Now, we've got magnesium that appears once on the left and one substance on the right. Nitrogen appears in one substance on the left and one substance on the right. So they're both easy ones. Which one's harder? Well, magnesium has 1 atom versus 3 atoms. That's a 1 to 3. Whereas nitrogen, it's 2 to 2. Well, that's going to be simple. That tells us whatever this number is, it has to be the same as this number. These two numbers have to be the same because the nitrogens have to match. So we might as well figure out how many magnesiums we need to make one of these. So we set that as 1, and we need 3 of those. So we have 3 magnesiums. We'll eventually make 1 magnesium nitride on the right side. So the only thing left to figure out is how many nitrogen gases. Well, we have 1 of the product. That means we have 2 nitrogen atoms. Well, that's enough to make 1 and 2. So we know the ratio is 3 to 1 to 1, and that's the simplest whole number ratio we can do, and there's the answer. And you'll notice we don't write the 1s when it's 1. If you write the 1, I'll still accept it, but it's considered better form to not bother writing the 1. We can see that there's 1. There's no point in writing that number. The next one, I'm going to see if you can do this on your own. I'll let you pause the video. Okay, and now I'll show you. Phosphorus and oxygen both appear in only one substance on the left and the right. And so they're both easy. And you have a choice of balancing the phosphorus, which currently is 1 atom to 4 atoms, or the oxygen, which is currently 2 atoms to 10 atoms. I would say the oxygen was a little harder, so I would balance the O2 and the product, the P4O10, or tetraphosphorus decoxide. So I have 10 oxygens over here, so if I had 1 of these molecules, I need 5 of these. So that will balance these two. I know this ratio is 5 to 1. That's set. It might be higher numbers, but the ratio will be 5 to 1. Now I know how many phosphoruses I need. I need 4 phosphorus atoms, so I can just fill in the 4, and now I know the ratio is 4 to 5 to 1, and that, in fact, is also the simplest version of this balanced equation. Sodium plus water makes H2 gas, hydrogen gas, plus sodium hydroxide. And you'll notice the hydroxide is a polyatomic ion, but it doesn't really appear as as hydroxide on the left side. It sort of does if you think of water as H bound to OH, but we'll wait until we talk about acids and bases to look at it in that way. For now, we'll treat them all as separate atoms, and we need to balance each of the atoms involved, the sodium, the oxygen, and the hydrogen. If you wanted to make a table first, you could make your table initially and see that the sodium is already balanced. I have one on the left, one on the right. The oxygen is already balanced. I have one on the left, one on the right. And the hydrogen is not balanced. I have 2 on the left, and I have 2 plus 1 on the right. Well, that's no good. So we know we have to balance this equation. Even if one atom is off, the whole thing is wrong in terms of balancing. So we know that hydrogen appears 2 times on the right side of the equation, so that is the hard one. The others appear only 1 time on the left and the right, and therefore hydrogen will be the last thing we're going to do. So it's a choice now between sodium and oxygen. They both appear once on the left and the right. We just pick which one we want to go with. So let's try oxygen first. We might have picked sodium. There's nothing wrong with that. If we picked oxygen first, we can compare the 2 oxygens. Well, they both have 1, so let's put a 1 and a 1 here, so we balance the oxygen. And that's fine. But now we know how many sodiums, so we can balance the sodium. So we know the ratio is 1 to unknown to 1. And so we've got 3 of them, 3 of the 4 done, which seems good until you check the hydrogen. And you notice on the left side, we have 2 hydrogen atoms here. And on the right side, we have determined we have at least 1 hydrogen here, but that's not enough to make 1 H2. We only have 1 hydrogen left to do this. Well, the only way to make that work would be to put a half there. Yes, a half of H2 would be 1H, but we know that we're not allowed to use fractions in our final result. So if we have a ratio of 1 to 1 to 1/2 to 1, well, if we multiplied everything by 2, so we change that to 2, we change that to 2, we change this to 1, and we change that to 2, now we have whole number ratios. It's 2 to 2 to 1 to 2 in our final balanced equation, and I'm going to clean this up and show you the answer here. It's 2 to 2 to 1 to 2, and that's one way to do it. But you notice you have to double everything. If you're going to double one thing, you have to double everything you've already determined the ratio of before you figure out the remaining coefficients. So this last one is iron 2 chloride plus sodium phosphate makes sodium chloride and iron 2 phosphate. So what's going on here? Well, we've got a number of things we have to balance, but I want you to notice this molecule, or this formula unit, has 1 phosphate, whereas the one over here has 2 phosphates. And the phosphate is not changing identity, so let's keep the phosphate together. There's no point in breaking it up into pieces. So we've got an iron to balance, we've got chlorine to balance, we've got sodium to balance, and we've got phosphate to balance. And if we look initially in our reaction, we have 1 iron on the left, 3 irons on the right, so we already know it's not balanced. We have 2 chlorines on the left, and we have 1 chlorine on the right. We have 3 sodiums on the left and 1 sodium on the right, and we have 1 phosphate on the left and 2 phosphates on the right. So which one would be the hardest to balance? Well, you'll notice every one of these 4 only appears on the left side, only appears in 1 formula on the left and 1 formula on the right. So they're all in the easy category. So which one's the hardest one of the easies? Well, we can either go with a 3 to 1 or a 1 to 3. So either one of the 2 metals would be where we're going to balance first. I'm just going to pick one. I'm going to delete that table for now. We'll come back to it later. Let's do sodium first. So we've got a certain number of sodium phosphates and a certain number of sodium chlorides. And you can see there are 3 in the first one and 1 in the second. So if I had 1 here and 3 here, well, now I balance the sodiums. That's great. Well, this gives us information here, and let's look at the phosphate. Well, we see that we have 2 phosphates on this one and only 1 on this one. Well, I don't even have enough phosphates to make 1 of this molecule. So that tells us that while this ratio of 1 to 3 is good, those aren't the final values. I have to double each number. So I'm going to double the 2 to 1. I'll double the 3 to 6. So I'm going to erase this and rewrite that. So we have 2 of these and 6 of these, and now we have enough phosphates to make 1 of these, and we have enough chlorines to make 3 of these. And now we know the final ratio is 3 to 2 to 6 to 1. Is there any way we can simplify this to a lower set of numbers? No, I can't divide it by 2 because the 1 will become a fraction. I can't divide it by 3 because the 2 and the 1 will become a fraction. So this is the simplest version, and we'll just show the final one here, and that is our balanced equation, and we'll stop here.